So I'm going to double click a little bit on what Adi mentioned as our reliability suite. I spoke with a couple of you during coffee, and it sounds like many of you are focused on maintenance, reliability, asset operations. So I will give you an introduction to what is our reliability suite, what is our version of predictive maintenance, what makes that different. I've included some customer examples, so how a select number of our customers using this application at scale to drive that business value that Adi was talking about. And then I have a short demo video of some exciting new features, the new release of our application. This is an application we've been working with customers on for 10 years. So what does the latest version look like? And then when we break for coffee, I or Sid can provide some live demos of the working software as well. By way of introduction, I am Lila. I'm responsible for reliability and sustainability with C3. We've been with C3 for about 5.5 years. I'm trained as a chemical engineer and came from oil and gas. I worked at BP in my first life. So our reliability and sustainability applications that Adi mentioned, he already described in some detail. One additional point to call out is these applications are fully interoperable. So where we integrate data and we connect to your systems, deploy the platform, the C3 AI platform, into your environment, the data we integrate to a single application, the first use case that we get started with, is instantly accessible and reusable by the other applications that share that same data. So we find this is very, very valuable with the applications in this portfolio. Typically, we'll start with a very high value, very tractable use case, something like predictive maintenance, C3 AI reliability, which is what I'll show you in a second. This is typically a relatively straightforward business case. Many asset operators face unplanned downtime, are hoping to reduce those outages and improve the reliability and therefore improve the output of their plants, make their plants more efficient, get more out of their assets. So start with a very straightforward business case like reliability. Once we've integrated that data, get that system live, then it is very natural and much faster and easier to scale to adjacent use cases. So then you have the data in place, you have the software working in place, you can then scale to something like yield optimization or process optimization to minimize the energy consumed, et cetera. Using C3 AI reliability specifically, this is a small handful of our customers that we have deployed the application with and who are using the application at scale. What you'll notice here is it's across a wide variety of industries. The way that we've built the application, the way we have deployed and created what we call C3 AI reliability, this predictive maintenance app, is extremely reusable across industries. So even though the way that transformers operate and the type of data that you use to monitor and predict failures on a transformer in utilities looks pretty different than the failure modes and the way that a gas turbine would fail in an offshore production platform in oil and gas, it's actually the same plumbing, the same pipes, and in many cases the same machine learning algorithms that we can deploy for both of those very different types of assets. And then at the end user side, the application itself, the core workflows, the types of insights, is actually also very similar. A reliability engineer or a remote monitoring engineer is looking for the same type of evidence. When I predict a failure, when the application is, or machine learning models are predicting failures, those users are looking for the same things. Why is that failure predicted? What are the underlying sources in the data that are predicting that failure? Is it a trend in a sensor? Is it a correlation to a prior failure event that we've observed in the history? And so maybe identify, what are those similar recommended prior events? What is the quality of the data, as Adi mentioned? Are there problems with the sensors? And then can I look at that? Can I really query, investigate, make plots out of it, time series charts or scatter plot charts? And then I want to go create a case or create a work order and take action with it and make sure that someone in the field is going to go and do something about this issue. And so that's the same general workflow, whether you are in industrial manufacturing, making paper, or if you're in utilities and monitoring transformers and circuit breakers. Our customers are getting some recognition from top analyst firms, so we're really proud of the work that they're doing. The customers here listed as a handful that are using predictive maintenance at scale, so just really proud of the work that they're doing. So what are the types of outcomes that we drive with C3 AI reliability? One is reducing unplanned downtime. 2 is increasing asset availability. 3, reducing maintenance costs. And 4, improving safety. So by predicting failures before they occur, you can intervene. And I'm excited to hear from Richard following our coffee break about how Shell is actually operationalizing predictive maintenance. It's a really common question that I get when starting to work with new customers is, today we work on a scheduled or planned-based maintenance routine, or we run to failure. We just let our assets fail, and then we go and fix it reactively. How do I, as someone sitting in digital or someone spearheading this digital transformation initiative to implement predictive maintenance, how do I operationalize that? How do I convince the business stakeholders to proactively take action, or is the better outcome that they stage the work? Instead of just doing routine scheduled maintenance once every 6 months, maybe they want to gear up the team and say, hey, we're predicting this failure. You might choose to run to failure anyway, but now you have the right team in place, you have the right parts and materials, the spares all ordered, so that once that failure does occur, you can immediately triage it and you reduce the total amount of unplanned downtime. So there's many different ways that our customers are adopting and operationalizing these insights. It doesn't necessarily mean 100% of the time you proactively take a machine down and do something about that predicted failure. But it does mean that at the end of the day, you're increasing that asset availability and reducing the total amount of downtime. I'm going to just linger here for a second on the types of data that we integrate. So Adi explained in some detail that we connect to your existing source systems, and we're actually unifying across different types of data that you wouldn't typically include maybe in a single data enterprise platform to run machine learning models. So traditional data, so what you see in blue, that's really the operations data. That looks like time series measurements, it looks like control set points, work order history. If this is in a manufacturing plant, what is the production history and upcoming production schedule, so you know what are those raw materials that we'll be running through, because raw materials may have a strong impact on the operation of the asset. And then we also integrate the non-traditional data, what you see in green. And that looks like unstructured text, so documents or diagrams, like engineering diagrams, like PNIDs that we parse using another AI form of machine vision to understand what is the relationship between any given sensor and its parent asset. What are the different relationships between assets? If I have a failure upstream, how might that impact something downstream? And so we unify that data and create basically a digital twin, if you will, of the asset in operation. What is the history of it? What are the failures that have occurred? What is the maintenance that has occurred? What is the metadata around it? Who is the manufacturer? What is the typical failure rate, the mean time between failure, as well as all of that contextual information about the diagrams, machine operating logs, maintenance manuals, et cetera. So I'll show a demo in a second, but before I do, I'll just give some examples of how this is actually working for our customers. So this is, just going back a second, this is a pharmaceutical manufacturer who came to us and said, we typically operate with scheduled-based maintenance, and their operations are very different than, say, an oil and gas customer, because they operate in batches. So they said, look, but if we have a failure in the middle of a batch, it creates a ton of scrap. And that is a huge amount of lost material, and we want to avoid that. So how do we, in our batch operation, predict and identify when the next batch is likely to have an issue? They were using some forms of monitoring, but those monitoring systems did not capture all of the upcoming failures. They only were able to identify the known events that they'd seen in the past and a certain subset of those known events. They didn't provide very much lead time. So we see this a lot in condition monitoring software where, yes, you may implement a condition monitoring system, but because it's based on either simple rules or hard-coded logic, it'll only give, at best, a couple minutes of advance notice. And with only a couple minutes, it's unlikely someone will notice that that alarm is running and that they'll actually be able to do anything about it. They had a hard time incorporating various forms of machine learning models. So we see some systems that do start to apply machine learning. One-class SVM models, very popular type of machine learning, okay. But it's kind of a one-size-fits-all approach. And so if your asset or your operations aren't really well modeled by that one type of algorithm, then it's not going to work very well for your machines and for your equipment. And so they were looking for a system that was more flexible. How can I run thousands of A/B tests that compare and contrast the performance of different types of AI algorithms on every single asset, where I might have a unique model per individual equipment? Per pump, I might have a very unique model across 1,000 pumps. And that allows you to get much better performance of the model itself because it's highly tailored to that asset. Even if it's the same model of the same pump that is coming from the same original equipment manufacturer, it still might have unique operating characteristics because of the conditions that it operates within. And so being able to deploy those different types of models uniquely allows for much better performance. So this customer is looking for those types of benefits. They unified data, as I mentioned before, things like work order history, what were the different alarms and notifications that they had received, the batch reports, so what are those batches that they were producing, the prior system alerts, and then of course the sensor data, the monitoring data from the condition system. We trained and deployed, as I said, we run these A/B tests. So upon deployment time, when working on initial configuration of C3 reliability, we'll typically train, I don't know how many this was, this is 500 different ML model permutations, which then you train across every single asset and identify what is the best performing model for every asset, and then configure the user interface. We do this over the course of a 3-month project, and then at the end of the 3 months give you access to get to use the system and actually start training end users. So it's relatively quick to get started with C3 reliability, and then as a result, really see the change to those operational KPIs. So some of the benefits that this pharmaceutical customer has now implemented is, this is really common, is just reduce the number of alerts that are generated per month. So many reliability engineers or plant engineers, process engineers are just flooded by alarms. I had that experience working in operations where you just start clicking delete on your email because it doesn't really matter. There's so many alarms, I'm never going to get through them all, so I'm just going to focus on when the operator is calling me, I'm going to focus on those issues. So instead, get much more precise about what alarms are being surfaced because those are the ones that matter. So this is a 90% reduction in the number of alarms that are being surfaced, which is very typical for most of our customers. I see in the range of 85 to 95% reduction in alarms typically. Second is an increase in the ability to successfully predict and identify failure events before they occur. So this is being able to notify those engineers before they start a new batch that there's going to be an issue and that they need to go do something about it before they start that manufacturing run. And then importantly, what is the lead time before the shutdown? It's only so good to recommend that, hey, there's a likely issue. If your good catches are still only minutes before that event, you still can't do anything about it. So being able to increase the lead time, going from a 45-minute, in this case, alarm, to almost 4 days of advance notice, makes it very, very actionable. You can actually go send and schedule a technician to go look at the asset, make sure that you have the right parts, and then go do something about it. So this customer started with us in the California area and then is scaling this solution across their various manufacturing sites. So they're starting with a single asset class. There are centrifuges, which is a really critical asset for pharmaceutical manufacturing as you purify biologics to produce some final drug. And then scaling with that starting asset across their plants globally before tackling their next asset class. A second case study, this is a major chemical manufacturer. So the challenges that they had were twofold. One is monitoring furnace health and optimizing decoking schedules. So furnaces are a very critical asset within their chemical manufacturing process. They had an existing furnace health monitoring solution, but again, it was very very rules-based and univariate. So it just looked at individual sensors and said, all right, if this sensor goes out of bounds, generate an alarm. Certain sensors are more critical than other sensors. You can couple sensors and say, all right, if both of these sensors are out of bounds, that might be a more severe issue. But again, it's still rules-based and it's still reactive. And then second, their decoking schedule was time-based. So you decoke a furnace kind of gets full of crud as you run it because it has all of these impurities in the flue gas that you're burning. And so then as those impurities build up, that's called coke, and then it makes the furnace itself much less efficient. And so you're not getting as much heat out of it because you have this thickness building up on the inside of the coils. And so you have to go through this lengthy decoking process. It's like 10 days of cleaning, and they were running this pretty fixed schedule I think every 90 days. And so they came to us and said, how do we optimize this? Because if actually the furnace is running well and that level of coke that's built up isn't so severe, then we can keep running and we can maximize the run length of that asset and get more out of it. Because the more times you take it down for that scheduled maintenance, you're losing 10 days of operation. So they came to us and wanted to do both projects with C3 AI reliability. Same thing, we unify, first step, unify, connect to their existing source systems, deploy into their environment, then train all of these machine learning models. In this case, we also added deep dives with their subject matter experts on a weekly basis as we went through this project. In this case, the coking models in particular were not something that we had done before with another customer. In order to make sure that, number one, those models are accurate, and number two, that those subject matter experts can actually do anything about it. Are they going to accept these recommendations? Are they going to have trust and belief in the system? How do we make sure that the application, once it's live, is going to be adopted? So we started that early with these weekly touch points with the subject matter experts, and then configured the user interface screens. What you'll notice in each of these case study slides, by the way, is that the user interface itself is very configurable. So because we have that platform that Adi was mentioning at the beginning, any one piece of the reliability application or any of our other applications is highly, highly configurable. That could mean, what are the source systems that we're integrating with? Yes, we have pre-built connectors. We very typically integrate with your enterprise asset management system, with your time series historian, with your work management system. But if there's another data store that we haven't integrated with before, we're very flexible. Our data integration layer allows us to connect to that source system. Likewise with the machine learning models, as I said, right? We have out of the box dozens of machine learning pipelines that we've seen work pretty well for the predictive maintenance use case, and we'll run through and train all of those models and identify the best performing models. At the same time, most of our customers now have data science teams who've been running POCs, and predictive maintenance especially is a very typical starting point for data science teams because it's such a proven use case. And so for those customers that have data scientists who've been working on this problem for some time, they may have a really highly performing model, but that model is sitting in a Jupyter notebook in some POC environment, and they haven't been able to scale and operationalize those models. And so being able to flexibly deploy those pipelines as part of the application is core to our architecture. And for some customers, they may have that perfect model for their most critical asset, for a critical steam turbine, but they haven't yet created those models for the rest of the plant. And so then you can mix and match. You can say, I want to use my golden model for my most critical asset because I've been working on that for 3 years. I just haven't been able to operationalize it. But then I'm going to use your out-of-the-box pipelines for the rest of the plant and kind of scale quickly there. And then finally, likewise, on the user interface, what you're seeing here is, a highly tailored, highly configured user interface that's showing the coils in the furnace and different types of alerts that we're generating, because everything in the user interface is also highly configurable. So yes, we have all of these 3 things out of the box, fully enabled, coming from C3 AI reliability, data integration pipelines, machine learning pipelines, and user interface and workflow. But again, all of that is highly tailorable to your organization needs. So with this chemical manufacturer, again, we saw and have seen very strong results. So on the left-hand side, it's kind of a detailed look at that coking model and the forecast, as I was describing before. So being able to forecast what is the coking buildup on any given coil, the large deviation between predicted and actual observed. So in this case, the purple is the actual coking buildup, and the blue is the predicted buildup. And so once we start seeing those deviations between predicted and actual, we're sending an alert to the user to say, hey, look, we were predicting that your coking rate would stay relatively flat, but because of the way you're operating this furnace, because of the raw materials you're using, because you're burning at a higher temperature or higher pressure, you're actually starting to see much faster coking buildup than typical, and you're going to have to schedule that decoke event much sooner than anticipated. So as a result, number one is they've increased on average the run length of these furnaces. On average, they're able to use our application to not have such frequent decoke events, not do it every 90 days, but instead maybe do it every 100 days. And then the asset utilization as a result of that, combined with just predicting unplanned outages and unplanned failures on kind of the rest of the assets surrounding the furnace itself, increase the overall asset utilization. So one final example, then I'll show a quick demo and we can break for some more coffee. But with a particular oil company that we've worked with, this is an example where they actually have taken advantage of multiple applications coming from C3 AI. So they started with the predictive maintenance use case and then very quickly scaled to process optimization in order to get more out of their operations. So the primary pain point shown in red here is that they were rate limited in their production operations by their gas compression trains. And so they said, all right, if we're rate limited, really we want to be able to get more out of those gas compression trains. One, by reducing the total amount of downtime, but two, we think that if we optimize the knobs, the set points of the operations here, we think we can squeeze more production out. So we deployed this application, and kind of cutting to the chase first in this case, we have demonstrated 2 to 4% increase in total production volume on these gas compression trains. And then two is by deploying predictive maintenance, they're able to really safely make those adopt those recommendations. So they know that they're pushing the asset harder. The set points that the AI is recommending is kind of outside the historical operating state. They're now operating in a kind of a new regime that they haven't yet necessarily done before, but they're able to make those incremental changes, take the AI recommendations for new set points, one step at a time, make stepwise changes, and then as things start to deviate from kind of a really healthy state of the asset operations and the risk to the performance starts to degrade, the predictive maintenance models are now flagging those risks and say, hey, you need to slow down, don't make those set point changes. We're identifying deviations in the health of the asset, and you need to monitor this or take action to avoid a failure. So in this case, almost all of the data that I showed before, it's identical to exactly what we deploy in C3 AI reliability. So they were able to first deploy reliability, train up those machine learning models to predict failures, and then using all of that same data that they had already integrated, go deploy process optimization. It's on the same object model, it's on the same application foundation of that asset digital twin that we model in C3. In this case, there was maybe one additional data source, I think the production rate, because we want to make sure that we're actually measuring the production rate through process optimization so that the demonstrated results and feedback into the system are taken into account. So just double clicking, I'm not going to spend too much time here. Happy to talk at a break about this. And Sid, I know, is also very familiar with this use case. But how does this get operationalized? Because it is a little bit more complex than just predicting a failure and then having a maintenance work order that you schedule to have a maintainer or technician go and inspect an asset or make a repair. Implementing process optimization and changing set point knobs requires an operator to go to the control board and make those changes. And we needed to deploy this in a way that worked in concert with existing advanced process control technology that is a closed loop system that automatically controls set points in a plant. So in this case, we've started with a human in the loop approach. As the users are getting more and more comfortable with the AI, and we demonstrate that, yes, they're actually implementing the AI recommendations, then we plan to transition to a closed-loop system. But in this case, starting from the top left here, the real-time data, so that's including the target set points, the actual observed measurements from any given sensor, and the production rate. Those types of data get fed into the C3 AI process optimization application and underlying optimization algorithm, which then recommends set points for the operations. In this case, we're really focused on a separator within the gas compression train, recommend those set points, which get surfaced in a shift-wise recommendation to a process engineer who reviews that, and they dive into the evidence of the application. When that recommendation is surfaced, they decide whether or not they choose to accept or not accept, which is taken as feedback, and so we can measure the performance of those recommendations. If they choose to accept, it gets sent to an operator, and that operator overrides the APC controls in order to change the set points. We've seen this work very, very well, and we're measuring how frequently the operators are choosing to accept. So there's two different people that are having to accept that recommendation. First, the engineer to send it to operations, and then operations actually has to go and change those set points. And so one thing we've really focused on over the past 10 years of implementing asset operation software is, what is that evidence? How do you make someone trust an AI model? Because implementing a black box solution just doesn't work. And then I mentioned this at the beginning, and one thing we found is really, really important is the combined solution here, where when we recommend set points, we're also predicting the likelihood of failure on that same asset. And so that makes sure that not only are you surfacing the evidence of why is an AI model making a prediction, but you're also enabling an insurance policy, if you will, a backdrop of safety to say, if you make these changes to, in this case, this is the medium pressure separator pressure. If you change those set points, in this case, a user accepted the set points 4 times, the AI risk score, which is really faint, you can't see this on the right-hand side very well, starts to spike. And so those stacked bars are indicators of the risk of failure of that asset. So they started to accept those set points. We saw the risk score spike and said, hey, back off, stop accepting the recommendations. And those two types of algorithms are working in parallel, and those two insights are surfaced in a shared user interface so that the user knows whether or not they should keep pushing the asset, change those set points to run harder and harder, or back off because you're running the risk of failure. So in this case, we again saw really dramatic results, just focusing on the predictive maintenance use case. Number 1, reducing the number of alerts generated per year. This is a really dramatic reduction versus their rules-based condition monitoring system. Second is increasing the speed with which someone can triage an alert. Typically, if I receive some condition monitoring alert, I'm going to have to go and investigate what are the other sensors and alarms that are running at the same time? What might be correlated? I might pull that up in my own process historian and try to chart this out myself manually. I'm going to go and look up the standard operating procedures. I'm going to try to triage, all right, if I see these types of behaviors, what are the likely failure modes? Let me build out this fishbone and see where I need to troubleshoot. So making all of that data accessible and exposed kind of in a contained evidence package, if you will, just helps the user make that investigation much faster so that they can drive action very swiftly. And then finally, in this case, this customer was using 7 different types of monitoring applications, software tools, to come to the same result. So not only were the performance of the baseline worse, but they had 7 different software applications to try to get to these same outcomes. And so we're reduced the number of software systems that those users have to use. All right, so finally, I'm just going to go really quickly because I think we're short on time here. But a utility example, I saw a bunch of hands raised in utilities. So this is one of the largest utilities in North America. We've been working them for many, many years. They've deployed C3 AI reliability for transformers and circuit breakers across their network. So the scale of this is pretty massive. 350 different users. We're monitoring over 30,000 different unique pieces of equipment. huge amounts of data and number of records that we're updating daily. So we ingest daily data and then predict failure of those transformers and circuit breakers. And for this company and many utilities, sending someone out in the field is non-trivial, right? Sometimes they're driving hours and hours, and so they need to have really advanced notice of when this type of work needs to be completed so that they can properly plan and schedule for it. So in this case, again, very similar story. We have identified basically a 48% reduction in number of events, of failure events that they experience. So actual events have gone down, so that operational KPI for the business has demonstrated a reduction in actual events that they're occurring. And our ability to predict those failures. So they previously were running on a scheduled-based maintenance approach where they just tried to go service as many of their transformers and circuit breakers as possible, but on a routine scheduled-based approach. And so they kind of scattershot, blindfolded, all right, it's been 10 years since I serviced this asset, I better go out and check on it. And so in this case, now they have a 98% ability to identify and predict which assets to go service, which means that they have a much more tailored service approach. So they're no longer telling their teams, all right, we're just going to batch-wise, we're doing this region this week, we'll go move everyone, second region, or on a scheduled-based, time-based maintenance strategy. Instead, they're saying, all right, we know specifically this transformer is likely to fail, we need to go service it. And so it is a highly precise approach to maintenance versus that kind of scattershot approach. All right, so I'm going to show a demo video, and then we can show live software demos during the break. But I want to highlight how we are now incorporating the generative AI capability that Adi talked about into the application workflow itself. So yes, C3 offers a standalone C3 Generative AI application, which is that Google-like search experience. But also we're taking advantage of those same APIs, of that same deployment architecture of the large language models to improve the performance and usability of our own applications. So in this case, what we're looking at is the C3 AI reliability application. So typical user would be a remote monitoring engineer or maybe a reliability engineer. They log in daily to see what are their most likely risks, where do they need to go triage and investigate what's going wrong. So in this case, we're looking at a gas compression train. We're seeing, all right, the lube oil system is really high risk. Oh no, I can't talk that fast. So I'm going to dive into the lube oil system. In this case, we're looking at one alert on the lube oil subsystem, and it's providing me the detailed evidence of what's going wrong. What are the sensors that are having issue? In this case, the lube oil supply pressure, the lube oil tank pressure. I could scroll down and see recommended failure modes because the application is looking at those failure mode libraries and giving indication of what failure modes are most likely to be attributing to this issue. My video paused. Is it still playing on your side? Oh. Yeah, it did. OK, we're back. So again, I'm scrolling down. I can see these top failure modes. But now with C3 Generative AI, I can have a much more interactive experience. I'm no longer just looking at the data, but instead I can query it and ask questions to make an informed decision about what should I go do about it. So I can click into this Ask C3 Generative AI option. I click Start a New Chat, and this opens the chat window like you saw before. And in this case, maybe I'm an inexperienced operator, like Adi was talking about. There's been a lot of turnover. I could ask, what's wrong with my lube oil system? And in this case, it's giving me a summary. The lube oil supply pressure is 31 psi higher than the predicted value and rising. So we're showing what did the AI predict the sensor value should be versus what is actual. And I can kind of understand where is this coming from. The source in this case is the time series data source. It's not coming from a file. It's coming from the actual observed sensor historian. And then I might be wondering, OK, well, that's great, but is this critical? Is this still within my operating bounds? Or is this starting to be abnormal behavior? Keeps pausing, no? It is? Okay. Give some feedback. Yes, I think this is a good insight coming from the generative AI model. Yeah, I think it's the video is getting stuck. In this case, we're applying the generative AI models to both the structured data and the unstructured data. So in this case, what we're looking at is an example of summarizing and surfacing information coming from time series data. And now we're applying the same generative AI model and search capability to combine it with unstructured data. So now I might ask, the normal operating bounds for the lube oil supply pressure are 25 to 80 PSI, and I can see what is the upper limit and the lower limit, compare that to the actual sensor values that we have available, and then it's telling me where is this coming from, in this case, the Sailor's Pocket Guide. So it's reading those upper and lower bounds from the pocket guide for this asset, so like a equipment operating manual, and then it's surfacing that on a chart overlaid with the time series data that's available. So then I'm now satisfied. I've kind of investigated the evidence of this alert. I think that it is real. I'm going to go and create a case. So now I've entered into the case experience of the application. A case is where I can really collaborate with other users. I can upload files. I can leave comments. Maybe someone goes and takes a picture. They'll upload it here. I can see what are the other similar events and alerts that have happened in the past, kind of all contained in this central workflow. So now within C3 Reliability, we had this case experience, we've had that for many years, but now we've introduced this generative AI capability. So again, now that I'm working within a case, I really want to know, what should I go do about it? Yes, the alert told me there's an issue, but I need to know what actions should someone take in order to prevent an upcoming failure. So I have the top failure modes. Those are being recommended from the application, coming from the failure mode libraries, what's most likely correlated. I could see, all right, this could be a lube oil problem, a bearing problem, a cooler temp controller problem, but maybe I just want to be spoon-fed. Again, I'm that new operator. How can I troubleshoot the lube oil supply pressure on the lube oil? Because that is the most contributing sensor that is deviating. It summarizes, again, this time coming from an operating manual. If the lube oil supply pressure is high, you can do the following, and it's giving me a summary of what is that standard operating procedure, and I no longer have to go look this up in a file store. Most likely, people don't even want to read it because it's pages and pages. It's like opening your car manual from your glove box. It's impossible to find the information you need, so let me just ask it here. I've already been focused, the application is focusing me on not only the most important asset, but the most important failure mode, what's driving that prediction, and now I can just go and ask and quickly identify what should I go do about it. So I'll pause there. Again, we can give some live demos of C3 Reliability or other applications, chat more over coffee. But if folks want to stick around now before breaking, I'm also happy to take some questions. Yes?
Well, thank you for your presentation. I was wondering, you talked about a failure mode library. So typically when I think of failure mode libraries in our company, it would come from FMEAs. Where do you get the failure mode library?
Yeah.
And is it automated, updated by the AI? So if there is a new failure mode, does it get fed back into the library so that the library gets bigger, or how is it done?
Good question. So for the first part, where do we get our failure mode libraries? We have in the application, from our experience with other customers, a couple dozen what I'll call asset templates. What is the operation of a pump? What are the expected sensors to see on that pump? What are the different failure modes and root causes of those failures for that pump? For some customers, our asset template library is sufficient. In other cases, even though we might have that failure mode library in our repository, maybe you come with other failure modes you want the application to model. So then we'll ingest your failure mode libraries, kind of incorporated into the the design of the model itself upon initial implementation and configuration, and so we can augment our failure mode libraries with yours. In other cases, we might be configuring the application for a completely new asset type we've never seen before. It's a highly specialized piece of robotic equipment for your manufacturing line, and it's kind of fine-tuned to your operation. In that case, we'll work with you to look at the format that you have your failure mode library in, and then we'll ingest that and kind of rely on your source system to be the source of that failure mode ground truth. Now, for the second part of your question, how do we learn over time? The application has many points of feedback. I didn't go through many of the workflows and screens just now in that little video, but we incorporate user feedback at many points of that workflow. So, thumbs up, thumbs down, is this a good recommendation, bad recommendation? Or thumbs up, thumbs down, we missed a failure. And if we missed a failure and it's because, it wasn't, the machine learning models weren't trained on enough data to be able to anticipate that failure, then users can give that feedback, and then we'll retrain the models in order to incorporate that in over time. So there is kind of a reliance on users to be giving some feedback, or we just typically our retraining schedule would be about once every 6 months. So then you could wait for the kind of routine retraining in order to capture those new failures. Yes.
Yeah, on that training of that model, to what extent do you use historical data, historical process data, and how do you single out the relevant events for that particular model?
Yeah, we do use historical data. It's not required to get started with C3 reliability, but we typically like to train our models on roughly 1 to 3 years of historical data. And then through that configuration project, we'll sit down with your SMEs when we're maybe a major turnaround event that would have been a massive regime shift, and we need to kind of treat those time periods differently. Or what are the periods of outages that we need to mask out? And so we'll exclude some periods of data when training the models. And so we work with your SMEs to understand that initial history. Now, if you don't have that history, then we can get started with basically an anomaly detection approach. So deploy really simply trained models. If there's only, let's say, like 1 month, you just deployed this sensoring technology, you've just set up your historian system, then we'll just deploy pretty basic anomaly detection models while we collect that data, and then we'll retrain those models over time.